In math, functions can behave very differently. Some of them are nice and smooth. Some have jagged points. Some diverge to infinity and come back. Some jump around, and others move really fast. It'd be nice to have a way to figure out these behaviors. Yeah, so that's what limits are for. Actually, they kind of only tell you what happens around a certain point or input value, and not really about the whole function or its behaviors. I just needed some sort of hook that's somewhat related to limits. Anyway, more about limits. So, like I said earlier, limits tell you what happens around a certain point. Specifically, they tell you what y value a function approaches as you get close to a certain x value. So like for the function y equals negative x squared plus 2x, the limit as x approaches 1 is going to be 1. Yeah, I know, it seems quite useless in this context, because the limit is just what the function is equal to. This animation shows a left-hand limit, by the way, because we're coming in from the left. In notation, it's written something like this. For the limit to exist, the left-hand and right-hand limits must be the same, but sometimes it isn't always this nice. Take for example, this piecewise function. If I were to ask you for the limit as x approaches 3, what would you say? See, it both approaches 1 and 5 at the same time. Specifically, it approaches 1 if you approach from the left, and 5 if you approach from the right. In limit notation, it's written something like this. It approaches 5 because the value of the function at x equals 3 is 5. No. When working with limits, we don't care what the value of the function is at that point. We just care about the value it approaches. You might be tempted to say it approaches 3 because that's the average of 1 and 5. No, because neither side actually approaches that value. So in this case, the limit does not exist. Like I said before, for the limit to exist, both the left-hand side limit and right-hand side limit must be the same. Here's a new one, composition of functions. Try this one out and see if you can get the right answer. If you did it right, you should have gotten undefined, which seemed intuitive from the graph of f of x. This animation shows that the left-hand and right-hand limits approach different values. The blue dot represents the value that g of x is approaching, and then we plug that into f of x, and that produces an orange dot. It shows intuitively how the composition of functions work. Alright, so this time we got another composition of functions. Yeah, so pause it and try it. If you thought the limit was undefined because the limit of f isn't defined at 1, you'd actually be wrong. This animation should help to show that as we approach x equals 7 for g of x, we only approach y equals 1 from the bottom, regardless of if we approach from the left or right. This makes it so that we only consider the left-hand limit for f of x, so the answer here would be 3. Here's one from the intro of the video, 1 over x. It's a popular example because of the unbounded behavior at the origin. If we were to try to solve for the limit as x approaches 0, the left-hand and right-hand limits both approach infinity or negative infinity, meaning the limit does not exist. Because for the limit to exist, it needs to be finite. We have our first and only rational function. I'm too lazy to come up with like other examples, and they all kind of work the same. Also, I'm not going to show the graph for this one because it'll just give it away. Yeah, so pause it and try it. Alright, so as you can tell by the graph, this limit is pretty simple. It's 1.5. The trick with these limits is that when you get the form 0 over 0, you should look for any factorizations that you can do and cancel out the factors. Like here, for instance, all you have to do is factor out x minus 3 from the top and bottom. Either you end up with something rational like we did here, or something like 1 over 0, and then it just counts as unbounded and the limit doesn't exist. Here's yet another one from the intro of the video, sine of 1 over x. The limit as x approaches 0 does not exist here because of oscillation. As you can see, it doesn't settle down on one value as you approach from both the left and right. Now we on to horizontal asymptotes. Not doing vertical asymptotes, since you can just like intuitively guess what they are from like the unbounded limit cases. That's what they are, by the way. Horizontal asymptotes look at what you remember as end behaviors in Algebra 2. When working with these, you can kind of like simplify any polynomial part down to its highest degree part, because every other degree kind of becomes like minuscule compared to the highest degree. So like taking the highest power term from both the numerator and denominator, we get this, and simplifying it a bit further, we get 1 over x. Now the horizontal asymptotes, you can just plug it in at this point, are just 0. Here's another horizontal asymptote question. If you want to try this out on your own algebraically, you need to pause right now. Anyway, we're going to do the same thing as last time and replace each polynomial by their highest degree term. It turns into this, and then it turns into this. As you can see, the asymptote is y equals 2 for both directions. I think I'll just leave it at that for limits. I might have skipped over some things here and there, but like I'm a little lazy to do that. This is like a good gist of what there is. Now we're just going to move on to continuity. It's pretty short and intuitive. Continuity is pretty simple. It basically states that for a function to be continuous, its value at every point must equal the limit at that point. Here, the pink dot represents the value of the function, and the green dots represent the left-hand and right-hand limits. This is a cubic function, and all polynomial functions are continuous. Any of the earlier functions we did where the limit did not exist at a certain point are not continuous, as the limit not existing fails to meet the requirement of continuity. There's also such things as continuity on an open interval and a closed interval. This is an open interval continuity, where the value of the function equals the limit for all values in the interval, excluding the ends. This is a closed interval continuity, where the ends are also included. To go from an open interval to a closed interval, you need to show that the right-hand limit at x equals a approaches f of a, and that the left-hand limit at x equals b approaches f of b. That's about it for continuity. Now we're just going to move on to some theorems. Our first theorem is the squeeze theorem. This theorem is about limits and uses other functions that you know about to figure out the limit of a function that you don't know about. Basically, if a function f of x is sandwiched between g of x and h of x at a point c, which is about like 2.5 here, and both g of x and h of x approach a limit L as they go to c, which is about like 1.75, then f of x also approaches L as x goes to c. Okay, that was kind of a mouthful, but it makes pretty intuitive sense if you just look at this picture. A good example of the use of the squeeze theorem is the limit of cosine x over x as x goes to infinity. If you plug in infinity, cosine of infinity doesn't make sense, but you do know that cosine is always between -1 and 1. If we divide by x, we can see that -1 over x is g of x, cosine of x over x is f of x, and 1 over x is h of x. Both g of x and h of x approach 0 as they tend toward infinity, so cosine x over x also approaches 0. The last theorem is the intermediate value theorem. This states that if you have a continuous function and you choose points a, f of a, and b, f of b, for all L within f of a and f of b, there exists a c within a and b such that f of c equals L. That was a mouthful, but basically, if you have 2 points on a continuous function, every value between those 2 points has to exist within the region of those 2 points. This is especially useful when you're trying to numerically calculate zeros. If you have 2 values of a continuous function, and one is negative while the other is positive, the intermediate value theorem tells you that the zero has to be within those 2 points. For this to work, the continuity of the function from a to b has to be a closed continuity. It has to be a closed continuity and not an open continuity. If you were to try to apply the theorem here on the interval -2 to 2, it would try to state that there exist all y values between 4 and -4. However, we can clearly see that the function actually just sits between about -1.5 and 1.5. The reason it didn't work here is because it was an open interval continuity. The limit at the ends did not equal the value of the function at the ends. Here's the application outside. Given these points on some function, at least how many zeros do you know there are? See, it switches from negative to positive down to negative and up to positive again. That accounts for 3 switches, meaning you know that at least 3 zeros exist within these intervals. This function of fit shows that it has to have 3 zeros. That's about it, I think. Limits seem pretty useless as of now, but they're going to be important when we get into things like derivatives or integrals. This is my first time making a type of video like this. In the future, I'm going to try and be making a video with like actual animations besides some like Desmos graphs with like equations and stuff. I'll try to make one before every unit test, but that might be hard. Yeah, I'll see. Yeah, alright, so make sure to like, and sub, and all that, and like leave suggestions in the comments and whatnot. And I'll see you guys like in the next unit.